Let's wait for a few more minutes before we start. Yeah, in case anyone who is joining. I think we should get started. Okay, so welcome everyone. I am Ayush Kumar Tyagi. I am PhD student at IIT Delhi. So today we will be looking at few of the questions. There was one doubt on the discussion channel about the dimensionality of CNNs and number of filters. So we will look into it, and we will look into previous assignment solutions, and then we will move to epipolar geometry and we'll try to solve few questions there. Okay, let's get started. So there was the doubt that what confusion is a number of output feature map when the convolving three channel image with 2D kernel. So let us revise what happens when we do convolution in a traditional manner. So in case of normal convolution, suppose we have a W cross H cross C image where W is the width, H is the height, and C is the number of channels. So when we convolve it like with a filter with a dimension of k cross k cross C, k cross k cross k, where yeah. Uh, okay, so we I just started discussing the doubt you had about the number of filters, right? Number of like convolution operation with 2D kernels. So before we move to that 2D kernel, let us see that like what is the normal way of doing things. So like in a normal convolution, you have an image with width comma height comma channels, and you convolve it k cross. Sir, you are not audible. Okay, let me just see. Am I audible now? Am I audible? Can you confirm that I'm audible? Hello, hello, hello. I can see the. Okay, so I'm audible, right? Okay, great. So, like, let's see what is the normal way of traditional way of doing convolution operation. So you have an image with width, comma height, comma channels. You have a kernel with k cross k, where k is basically equal to number of channels in the input image, right? And you do convolution operation, you get w dash h dash and cross one. So everything boils down to like a single you get output in a single channel output with w dash depending upon what is the padding, what is the stride, right, and height is w h dash, right. This is the traditional way of doing operation. So like in if you look into the PyTorch, so if you say that like if you say that like you select the kernel 3 cross 3, this the third channel, that is cross 3, is implicit in that operation. So if you select 3 cross 3, this another 3 is also taken care of by the PyTorch. So that like the operation is 3 cross 3 cross 3 with the input image which has a suppose dimension 500 cross 500 cross 3, right, and you have a resultant which is a single channel. So suppose you have c dash kernels, right? So what will be your output in that case? So with first kernel you'll get w cross w dash cross h cross 1, and you have c dash kernel, so that like now you have c c dash outputs, right, and you concatenate them into one single tensor. So your output tensor becomes a w dash cross h dash cross c dash, and this is the normal convolution operation, right. So let us see what will happen in the case of 2D convolution. So uh, in 2D convolution, you have a kernel which is only k cross k, and you are convolving it with an image of w cross h cross c, right. And that in that case you will have w dash cross h dash, it's your width and the height. And what you do is like since you have a single dimensional kernel, you will convolve it with each channel. So now you have a representation of each channel. So your output will have c channels, so if because there are c channel in the input image. So and you have the kernel which is k cross 1, right. So for every channel you will be getting a output of a convolution, this output of this convolution operation, right. So uh, this is a special case, right. uh, Special case, and this operation is basically seen in one of hello, you're saying something. Okay, so this yeah, okay. So suppose you have 40 filters, that was your question, right? Like you have 40 filters and you have the input dimension of 1024 cross 1024 cross 3, and you have a kernel which is a 2D kernel. In that case, you have your like output response would be your, suppose you're ensuring that the image dimensions remain same. So 2024 cross 2024 cross like 3 for this input channel, and there were 40 such filters, right? So 40 into 3, so your output dimension will be 1024 cross 1024 cross 120. But 40, right? Because what will happen is, like everywhere, this 2D convolution, in the 2D convolution, people actually perceive in a way that like the third dimension is implicit. So whatever the dimension is your kernel is, that is also extended to in the depth as well, right? So then only you will be able to convolve it. Yes, so that is the general assumption. Yes, so that's the case always. So assume, no, so you will have values for all the 27, right? Yeah. Yep. 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 So this third channel is kind of implicit always. So you have width, height, and this is your depth, right? Depth is taken care of this. Okay. Uh, in, yes. No. So no, like I'll just clarify. Uh, so the traditional way, whenever someone is asking you in exam, what they generally mean is this. Even if they represent it by k cross k only, right? So what they actually mean is like k cross k, where this k actually matches your number of channels. Then only you will be able to do a convolution operation, right? And this c in our discussion will be 40. So your output will be w dash cross h dash cross 40, where 40 is number of filters. This is true. Like this is true for the most of the cases, right? And most of the people who you might have referred to are following this convention only. However, whatever you have asked, that is also not wrong. So I'll go to that part, but we should just conclude and clear this doubt. So that conventional way of like number of filters is basically is proportional to number of channels, right? And the third channel in this filters is basically uh, implicit. Yep. Why? So suppose there is 6 c dash is, why so? Mm-hmm. C is 3. C is 3. And no, wait, let me just like take another pass on it. Yeah. So all of them are 3D. So W cross H cross C. 3 is the number of channels you have, like RGB. You have in the first layer, you will have a convolution like filter, which is K cross 3, right? And you do a convolution, right? Now, so yep. So then in the next layer, you'll have a filter which is have a dimension 3 cross 3 cross 40. So this always matches your output, right? Okay. Filters were increasing, right? Yes. This is, so what will happen is, this is your first layer, right? This is your input layer. This is your input image. You have the first like you have first 40 filters, and each filter have a k cross k dimension, right? But implicitly what it's meaning is, like, you have k cross k 3 dimension, right? So this will result into w dash cross h dash cross 1, this one convolution operation, this, right? Right. And one filter. Now we will be using 40 such filters. So what we'll have is, you have another feature map, right? You have another feature map, and you will have 40 such feature maps. So this dimension become 40. So your essentially your final dimension become w dash cross h dash cross 40. So this is your input layer. This is clear, right? Now when we move to the second layer, what we'll do is, you will convolve with 3 cross 3 cross 40, then you will get a output of w double dash cross h double dash cross 1, because you are convolved in only one filter. You get it, right? It will be your based on your padding and the stride, right? Let us assume that, like, w, yes, let us assume that, right? And now what you will be doing in layer 2, you will be learning 40 such kernels, right? Maybe more, right? Like maybe 80 such kernels. So eventually what will have the final output? You have w double dash cross h double dash cross number of filters you are learning, maybe 80, 40, whatever number of filters you are learning in that stage. This is, So all the 40 channel, because you have, right, you're talking about this region, right? Yes. Yes. Mm-hmm. No. So there is no first channel here, right? So the channel, let me just like try it again, right? So this is your kernel, right? So you have all the pixel values are there, right? So suppose it's a zero kernel, zero or like maybe one kernel only, right? So what you are generally seeing is like only one dimensional view of this. Sorry, two dimensional view of this. So you have only 9 parameters, but essentially what it has 27 parameters. What were you doing is like you were like multiplying this. Yeah, so 1 by 27 will be a normalization factor, and for every parameter you will be convolving it with your like input. Yes, this is clear, right? Now let us see at what will happen in the 40 channel case, right? So you have 1 cross 1 cross, right? This is your 2D view. Now you will have parameters in dimension 40 like you have in the depth, right? You have 40 such filters which are stacked, and this is your one filter. This is your one filter, right? So now what will you doing is you will be dividing by 3 into 3 into 40, and you will be multiplying every parameter of this filter with the parameter of your input, that is this, right? This is your one convolution operation. You get it? So now you will have w dash cross h dash cross 1 as the output. So this is your one convolution operation. Now you will do 40 such convolution operation. Maybe 40, maybe you're like confusing 40. 360 parameters. Yes. Ha ha ha. Okay. Ha ha. Yes. Yes. So what will happen is it will start with here, from here. This is your one operation. This will result into first item of this block, w cross w dash cross h dash cross 1. Then it will move this place. Then no. So when you are at layer 2, whatever the input to the layer 2 will be your convolution operation. Yeah, it's a feature, right? Like suppose this is the tensor w cross 40. No, it is output of layer 1, no? Suppose this is your layer 1, right? This is the output of layer 1. This is your output of layer 1. Now we move to layer 2. Now you do a convolution operation on that, 3 cross 3 cross 40. What will it result? It will result in w cross w, sorry, w layer layer 1 will have 3 cross 3 cross 3 kernel. Yeah. Now suppose, so you see, if you have you're doing a convolution operation and input is RGB, and they're saying that convolve with 3 cross 3 kernel. Just assume that you have a depth of 3. Depth should always match, then only you'll get a output. Okay, okay, I opened it. Okay, I hope. I think you cannot see my screen. I'll just read it. Suppose you have 40 convolution filters of size 3 cross 3 with padding 0 stride 1 in the first layer of the convolution. You pass the input to the dimension input of the dimension 1024 cross 1024 cross 3 through this layer, right? What should be the dimension of next layer, right? It has to it will need to have 40 as a like convolution kernel. It's in the first layer. No, not the 40. So you have 40 kernels, and with each kernel has a size of 3 cross 3, right? So what it maps is, let me just solve this question, right? Into 1024 cross 3 is your input. You have a kernel which is 3 cross 3, right? And you have 40 such kernels, right? 3 cross 3, 3 cross 3, 3 cross 3, right? What it essentially means is your filter size is 3 cross 3 cross 3, right? Now you'll have some output. Let us say like you have 204, I'm just guessing, 2021. This is your width and height, suppose, huh? And your, because you have 40 such filters, you'll have 40 in the channel, because for each convolution operation you'll have 1021 cross 1021 into 1. You, am I audible now? Hello. Swati, is it clear for you, or like I'm kind of confusing it? Yes, yes, you are. Am I audible? I am not audible. Swati, I am not. Am I audible? To hello, 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 hello. Am I audible? Hello. Mm. Let me just see if I can just disconnect my. Hello, hello. Am I audible now? I am getting an echo. Hello. Hello. Hello, 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 hello. Okay, perfect, perfect. So I mean, let's go step by step, right? So we have an input 1024 cross 1024 cross 3. We have just a minute. Okay, so you have a 3 cross 3 kernel, right? That's what they're asking in the question, right? You have a 3 cross 3 channel. What it essentially mean is they are convolving with 3 cross 3 cross 3, and you have 40 such kernels, right? So for one operation, what you will have is like, for this convolution of, right, you got it, right? Like you're convolving with 40 such kernels, and each convolution operation will give you some width, height, and number of channel will be one in that case, and you're doing it 40 times. So now it's clear, right? Okay. Okay, so let's move ahead right now. um, okay, so I mean, what question you have asked was not wrong. So there are cases where you do a two dimensional kernel convolution operation as well, where you have k cross k as well, right? So if you do k cross 1 convolution, you have to consider each channel as the output. Now you'll have the output as equal to the number of channel in the input. Earlier we were getting number of channel as 1, right, in the output. C was 1, right? If we do a one convolve with one convolution, one filter, right? But now if we are doing only 2 cross 1 operation, you will have output as W dash cross S dash cross C, because you will now have output for each channel. You got it, right? Then you get this 120 in the output. But well, like, this is addition to what has been taught, right? Like, but the traditional ways is that, like, you should get uh, like 1024 cross 1024 cross 40 as the output. But this is some special case, right? So this special case is basically called as the depth wise convolution. Since you have asked, I thought, like, for completion, let us see if that operation can be used anywhere, right? So what you do in depth wise operation, you learn a filter for each channel instead of learning a filter for all the three channels, right? Which is k cross 3. In this case, you are basically learning for all the three channel. Now in what is happening in depth wise operation, you are learning a filter for each channel, and uh, you what you do is, like, you do a point wise operation where you learn a 1 cross C filter, which is C, where C is 3 in this case, and you will learn n such filters here, right? You will get the same output as you would get in the traditional manner. So, but why people generally do it? Because it's a more efficient way of doing it. So there are papers which actually use depth-wise convolution operation, because the number of computations required to do a depth-wise convolution is less than the traditional convolution operation. So I'll just show you a diagram for that. Like, we will compute that, but I hope this is clear. So what is happening is, like, you have three channels, right? Channel 1, channel 2, channel 3, and you are learning three filters for each channel, right? You will get output of like response for each channel, right? 1 2 3. What you do, you concatenate all the three channels, and you do a pointwise operation where you are kind of learning how do you sample from the channels. So you have a dimension 1 cross C, where C is 3 in this case, right? And you will get output of 1 cross 1 cross, sorry, you will get output of W cross W H cross 1, right? This is your depth-wise convolution operation. So let us see what how uh, what are the number of parameters in the normal convolution operation. Suppose you have an image which has a dimension dg cross dg, and you have m channels. You have a filter which has a dk cross dk dimension, and it will also have m channels, right? So what will happen is your total number of multiplications will happen in dk square, right? Because you have 9 parameters there, you multiply with m, right? So this is the number of operations, multiplications which are required for convolution of one filter. This is at this place, right? This place, dk into m, right? And when you traverse through the image, you multiply with dg into dg, right? Yes. And you have like if you have k kernels, then you multiply everything into k, right? This is your total number of multiplication or computations what will happen in this case, right? Now if you go to depth-wise convolution, but let's approximate. I mean, the scale is completely different, right? Just yeah. So the order will be completely different in this case. so, so in depth-wise convolution, what will happen is, like, suppose you have dk cross dk kernel, right? And here the number of channel is 1, right? Dk cross 1, and you have m such filters because you have to traverse through the channel. You are learning a filter for each channel, right? So now what will happen is you have the total number of computation here is dk square into dg square into m, right? So this first filter will convolve with every like component of channel 1, right? So the number of operation will be dk square into dg square, right? And you do m such operations, right? For each channel you have a different filter, right? So that becomes dk square into dg square into m. This is your step 1. So this is your first part, right? This depth wise operation, right? Additionally, what you generally do is you do a point wise operation. In point wise operation, what you do is, like, you are kind of learning 1 cross m, this filter you are learning, right? In that case, what will be the number of computation? You will have dg square into m operations, right? Because you are traversing through whole image and checking for m, right? Your So what will be this? So this will be 1 cross, and you have a m as the dimension depth, right? You're doing it on right, the output basically. You're doing this operation, right, on this. Make sense? I didn't get it. Can you just repeat it? No. dg square cross m. No. So but we will do n such filters. We will learn n such filters, right? Like we have learned n such filter in the normal convolution as well, right? And n kernels we have learned, right? Here we have learned n kernels, na? So now it has to be equivalent to n kernels, right? We will be computing the total number of computation based on n kernels, right? So you have n kernels. So what is the total here? So you have dk square, which is coming from depthwise operation, and this is coming from pointwise operation. This dg square m into n. Right? If you sum it, you can basically take dg square m. Right? Hello. Your voice. Yeah, I think there's some issue with the voice. Let me just say that what is happening in the pointwise operation. In pointwise operation, we are computing a convolution operation with each for each pixel through the channel, right? So for pixel number one, we are computing what is the value effect of each channel, right? How do I sample each channels, right? That's why dg square, that is your dimension of image into m. Can you just write in chat? I think I'm not there's some issue. Your voice was not like it was breaking actually. Right, but the whole point of pointwise operation is to get a sense that which channel is important, and I'll just take that channel information, right? And if you do addition, you'll have dg square into m. In the bracket, you have dk square plus n, right? So as compared to what we were earlier getting dg square k square m into n. Now we are getting dg square m dk square plus n, right? If you do compute a ratio, the ratio will turn out to be less than 1. So essentially what is happening here is we are uh, like using less number of computations, right? And this change is basically coming when you're because you are doing a depth wise convolution operation, right? In that case, you are not learning k kernels, you are only learning 3 kernels for each channel. And you're the what do you say that like you are kind of learning the importance of each channel with pointwise operation. Although I mean this was just for the completion, right? Like you have asked the question, and that's why I thought like I think we will complete this discussion. So whatever the question you have asked was not wrong, so there is one way of looking into the convolution operation in using this depthwise operation. So yeah, next is it fine, right? Yeah. So next, I just wanted to quickly look into what was the solutions for quiz, right? Which have you submitted this, right? Like it was last week, right? Uh, yeah. So I think I hope you have submitted. Otherwise, I'll be giving out the solution. But it yes. So yeah. So in the first question is to anyone who's watching it later. So uh, we'll just quickly go over all the solutions, right, and how you are actually coming into it. So if homogeneous coordinate system has n coordinates, how many coordinates does the corresponding Euclidean system have? So for 2D system, let us say you have a point x comma y which is in the Euclidean space. So in the homogeneous coordinate space, you have x comma y comma w. In generally, you write it x comma y comma 1, right? So you have here you have 2 coordinates, here you have 3 coordinates. Similarly, if you have 3D system, you have uh, 3 coordinates here, and when you convert it to the homogeneous coordinate, you have 4 coordinates here. So in case where in the homogeneous coordinate you have n coordinate, in the Euclidean space you have n minus 1 coordinates. Okay, so next is how many unknowns are there in the 2D projective transform, right? Like if you remember, the 2D projective transform is basically you have x and you are multiplying with h here and you are getting x dash, right? So what is what is happening here is what you do is like if you scale everything by this last coordinate, right? So you're basically converting everything into the homogeneous coordinate space. Now this become one, and apart from that, like now you have become eight unknowns are there. How many point correspondences are needed for computing 2D affine transformation? Right. So how do you write a affine transformation? You have a1, a11, a12, a21, a22, and you have a translation operations as well, tx, ty, and the last one is 001. Right. So suppose you have a point x, right, and you are multiplying with the affine transformation matrix, you will get x dash. Right. If you write the equation for this, you have x dash is equal to a11x, a12y plus tx, right? So you are just doing this kind of a xy, xy, xy1. Okay. So you will have corresponding points for x dash, y dash. Similarly, like similarly you do it for other like points as well, x2, y2, x3, y3. So now you have basically the thing is like you have six unknowns, right? So you will need six equations to solve this. Six unknown, six equation, you will solve it using the matrix operation, right? You'll be able to solve it. So the number of points required is 3. So 3 xy pairs are required, maybe x1, x2, x3, and each has a x comma y representation. Okay. So next is a 2D geometric object is scaled related to the point with coordinates 2 comma 3 in x coordinate by 3 times and y coordinate with 5 times. Which of the following is proper order of matrix constitute this transformation? So this is basically relative to what? So relative to the center, right? So what you do is like when you do a relative transformation, you map it to the origin. So for mapping it to the origin, you are not doing any rotation, right? At this point, these are the components for the rotation, these are the components for the translation. So you are translating it back to the origin, then you do a rotation operation, and then you translate it back to the original space where it was, right? So now you are now if the final order should be in this order, right? So first you, and whenever you're doing a these set of operation, you move from left to right, right? So you translate it back to the origin, do the rotation, and now back to where it was, right? So if you see that, it will be there in the options. Right. So next is which of the following is the correct representation of projection matrix P? So the projection matrix P is basically defined by the this is the camera intrinsic matrix R, and you have uh, you have I, which is the identity matrix. It can identity matrix, and this is your basically the change in your principal points basically, right? So k is basically represented by camera coordinates. So k is basically represented by fx, fy, s is your skewness, and these are the principal points, right? And if you do and this c basically ensure that like your camera coordinates are at the center, right? Like you want to align your camera coordinate, then this c will take a translation into account, right? So generally people write this everything as the t as well. So p is equal to k r and t as well, right? So which of the following correct representation of projection matrix? I think this is you here k I have defined, r is basically in this order. This translation component is taken care of basically from world coordinate to camera coordinate. So if you want to translate any point from world coordinate to the camera coordinate, so that the everything is at the center of the camera. You're seeing everything from the camera point, right? So the camera is basically should be at 0 0, right? So if you want to do such translation, this matrix basically helps. Okay, so next is the minimize ah with subject to such that like the norm of h is equal to 1, right? So this is covered in the class to some extent, right? So what is happening here is you want to minimize ah, the norm of ah, such that like the norm of h is equal to 1. So what you do generally is you move it to the metric space, right? So what you do is like you write it as ah transpose uh, ah. So anything, right? Suppose a norm of 2 can be written as a transpose a, right? In this case you have ah, so you will write it as ah transpose ah, right? And this is a property of whenever you're doing a like whole transpose, ah transpose is equal to h transpose a transpose, right? You just feed this property here, you'll get h transpose a transpose a into h, right? So now what we can do is like we can do a svd, a single value decomposition of a matrix, and once you do that you will have u sigma v transpose. And there are two properties if you know svd, that u transpose u is 1, v into v transpose is I. So this is the identity matrix. What you do is like you just feed this a into here, what you get is h transpose u into sigma into v transpose whole transpose u sigma v transpose into h. You will use the property one again, so what we get is u v transpose sigma transpose u transpose into u sigma into v transpose into h. So this basically becomes identity matrix. So now what we have is h transpose v sigma transpose sigma into v v transpose s. So this is so if this is the like your matrix for which contains the eigenvalues, right? Suppose let us assume that like this is just identity or just one, right? So the whole equation basically solves to one. In that case, like suppose this you eliminate on this part, right? So the v into v transpose becomes 1, so identity, and h transpose h is basically 1, right? So everything is dependent on this matrix sigma transpose sigma, right? And to if you want to minimize the whole value, what you need to do is like you just need to pick the least minimum value for of minimum of this sigma transpose sigma, which is your minimum eigenvalue. That was your answer. Any doubt in this case? Okay, let's move ahead. I think this question, I think is the similar question we did in the last session as well. So, which of the following does not affect the camera intrinsic matrix? So let's recall what is the camera intrinsic matrix. So, camera intrinsic matrix is given by K, which you have the focal length component is there. You have the skewness component is there. You have uh, principal points are there, right? So first option was the focal length is directly present, right? Second one is the offset in the optical center, which is taken care by the principal components, right? We also saw that the image resolution actually affect your principal point and your focal points, right? and so the only thing which was does not affect the camera intrinsic metric is the exposure time, right? Because the focal length is same, your points are same, how long you give the exposure, it's not going to change the way you look into the image. I think this question was something, I don't know whether it was covered in the class or not. I don't think it was covered in the lectures, I guess. Uh, so find the focal length y for a camera intrinsic matrix if the image size in the x and y direction is 640 and 480 pixels respectively. The field of view of the camera in y direction is 45 degree, right? So you have an image size which is given to you, and we are basically interested in the y direction, right? Fy, right? And also there is the field of view is in y direction. So the formula actually says that the tan h of field of view by 2 is equal to width by 2 divided by the focal length. If you just reshuffle everything, the focal length is equal to w by 2 into tan of field of view by 2, and if you try to solve it, it comes out to be something, yeah, just check, but you just, yeah, you should be able to figure it out. I think this was not covered in the lectures, just maybe I'm wrong, just check. Okay, this is question number 9. Even what about question number 9? Were you able to get it right? For me, the solution is coming out to be slightly different to what the answers were. Like any of you give it a try, or were you able to get it? Question 9 and question 10. Hello, am I audible? No. Okay, okay. Let's give it a shot. Give it a shot. Okay. So the camera is mounted on a car, right? So maybe there's a car where camera is mounted on the top, right? A point S on a signpost. So you have a signpost. There's a point S, right? The location of the point in the world coordinate is this one. So you have a point which is as a coordinate of 1.5 and 9, right? The location of center of world coordinate system related to the camera optical center, and the camera frame is translated by t. Basically the translation is given by -1 -2 -10, right? And there is a rotation as well, uh, right, which is in the 180 degree on the horizontal plane. So there can be, so suppose what is happening is, suppose you have a camera and you have a x y z coordinate. Let us just write this x y z coordinates, and there is a translation between them, right? Like this point and this point, there is a translation of this -1 and -10, right? Right, and you have, suppose, and but the actual how the image is in perceived is basically the rotated version of this camera, right? So you rotate it along the x-axis. So you, let's say this is your x now, this is your z now, and this is your y now, right? The either the, so the camera is basically is present here, but it's present in the some sort of a rotated version. So if you want to get the actual correspondence, you want to rotate it along the x-axis, right? And the thing, it has been translated to, so there is some translation metric which is given. So you are getting an image of a signpost, but there is a translation between the point and a camera, and the camera is also in a particular rotation. In this case, there's a some sort of rotation is mentioned. So what you need here is you want to uh, get the position of the point S in the coordinate camera coordinate space, right? So let us say that like you have a S, right? You have a T matrix as well. So this is your translation metric, right? And you have a rotation which is along the x-axis, and the rotation is basically 180 degree, right? So if you look at the rotation matrix, it can be given using the cos theta minus sin theta cos theta, right? And so cos theta is basically cos theta, cos of 180 degree is minus 1, right? And sine 0 0, and this is 1. mm, no, I don't think so. This is in that manner. Let's just retry it. So you had a xyz plane, you flip it along x-axis, your y become negative, your z also become negative, so both the directions become negative, and your sine is anyway 180 is 0. So I guess r, your rotation matrix should look something like this: 1 0 0 0 minus 1 0 0 0 minus 1. You have a point, you want to rotate, like you want to multiply that point with the cos theta sin theta. Cos theta is minus 1. I think that also makes sense, right? But I think we are, when you're actually doing it in the cos theta sin theta sin theta cos theta, so everything becomes out to be 0 0 0 minus 1 0 0 0 minus 1. I guess this should be because of the rotation in the y plane, right? So this x plane, sorry. So that's why. Makes sense, right? The rotation is in the x plane, right? You can actually check. I think we can discuss it again. Just check it. I think it should be in this format. So what you do is, like, for you just multiply it with the rotation metric and adjust for the translation it has, right? So rs plus t should be the case, and you do the translation, it should get something like this. But I guess the answer was 0.5.51, right? So I don't know how that answer is coming out to be 0.5.51. I suppose your rotation matrix is this, something like this. 9, and then you are doing minus 1.5 minus 1.59, and you're doing negative. I don't think, I think I'm getting this answer only. So 0.5 minus 3.5 and 19. So I mean, just anyone just check and just comment in the discussion if you are able to get this, right? Otherwise we can actually talk to the instructor and get it rectified, right? And this you can actually write it in the matrix format. So the projection matrix where you concatenate T with R, it's a 3 cross 4 matrix. You have the point which is in 3 cross 1 space, right? In order to make it, you just put it into the homogeneous coordinate space. So 1 0 0 0 minus 1 0 0 0 minus 1, and concatenate the translation part and just concatenate 1 at the end too, so that like you converted the Euclidean space into the homogeneous space. You have S dash, right? S dash is basically coming out to be the same. Just check whether you are able to get this. So the correct answer was 0.5 I guess. But if you are able to get it, let me know. But my answer is coming out to be this. What is your take? I mean, were you able to get it, or like anyone in the chat, or want to say anything about it? Didn't understood the question. Okay, but now you understood it, right? Like what is happening here, right? What is required? So there's a point you just wanted to uh, make some sense. Okay, you just want everything to project it into the camera coordinate space, right? Like there is something is happening in the real world, so you want everything back in the camera coordinate space. Just see like once you go back, just see if you are able to solve it or now, right? So basically what so now they're asking is like everything is in this millimeter, right? Millimeter is not in the pixel space. You want everything to be in the pixel space. So what you do is like you have a K matrix, which is your camera intrinsic matrix, that so that like you can project everything into the pixel space. So what you do is like this P, which is you have learned, you have defined P here. This is the projection matrix, right? You multiply that point with P, right? And then you multiply it everything into with this camera intrinsic matrix, so that like you can get the S, which is the point in the camera coordinate space, in the pixel, the location, right? Basically, so we have just computed PS. I think there was similar question which we did last time. I'll just show you, right? There was this, we were actually kind of projecting everything back to the pixel space, right? Here also we kind of multiplied K into P into this was your input point, right? Last question which we did was like we were required to compute K. Here the K is given, we just wanted to compute the P, right? So what you do is like you, let's say this is P dash, you multiply P dash with K, you get something, but it is still in the homogeneous coordinate space. What you do is you divide everything with 19, which is the last coordinate, by 19, 10800 by 19, and this is 1. You can now this you can basically call it into the Euclidean space. So I am getting something close to 260 into 5, 620 into 560. But I think the answer was something 720 something, 960, 720. So just check it. I think everything boils down to this P dash computation. If you are able to get the P dash computation correctly, we should be able to get the second question. So just see if you are able to get the P dash correctly, and let me know, so that like I think we can take up this question in the next session, and then maybe others also get benefited from this. Okay, so about next is basically we'll be moving toward the epipolar geometry. So have you seen the lectures from the epipolar geometry? Because the things I'm going to discuss will be dependent on that. Anyone? I haven't watched these lectures present. Okay, so let's take a break for. I'll just show you. I just created a notebook for you, right? I mean, we went out without basically running it. I just wanted to show you how what are the parameters. So suppose you have the image which is 1024 cross 1024 cross 3, right? And one such image in the normal convolution, if you have outputs channel is equal to 40, right? So you're basically doing 40 such convolution. Kernel size is basically 3, so 3 basically take care of everything. So the kernel size 3 cross 3 cross what should be the input size of the kernel. So input channel is basically 3 here, so the output should be 3 cross 3 cross 3, and it should get something 1 cross 40 cross 1024 cross 1024. Whereas in depth wise convolution, where only the first part, uh, like uh, like before, in the initial we were discussing, right? So the number of channels is, input channel is 3, output channel is now uh, 3 into 40 120 channels, and kernel size is 3, but what you're doing is that we are doing it a group of 3. So now uh, like it doesn't take into account the whole uh, depth, right? So it will do it to only like for each channel you will have output. So your output becomes 120 cross your input dimension. Just wanted to show you this because like any doubt you have, you can basically go back to your coding and just see it yourself. Just implement it and see. Let us solve few questions of epipolar geometry. I think then we'll close. So what is epipolar geometry? So what is happening here is like you have uh, a point and you're taking pictures of that point from the multiple cameras, right? Like there is one camera here, there is one camera here. So how do you correspond between these two cameras? So how the picture is formed from one. So what is the correspondence of one the point, any point on this camera to the any point on the other camera? So that's what the epipolar geometry. So based on this translation between these two camera, how the things are going to change, and there is a way where we can actually map this any point from this camera number 1 to the camera number 2 using this epipolar geometry. There is something called the fundamental matrix that is used for that. I mean, there is a YouTube video also. There is a very fun song. Just type search it, fundamental metric song. That basically boils. It's a kind of a rap for this epipolar geometry. It's fun. Uh, yeah, in one of the conference, that guy actually like gave that sang that song in the closing ceremony. It was fun, right? So yeah, weird ways of learning things, but effective. Just have a look into that, right? So uh, this is basically when where the two camera planes are parallel to each other, so both of them are kind of this in this way rather than this way, like, right? So in that case, these E are the called as the epipole point, and whenever, so suppose this, sorry, this was your plane, right? And the point where this uh, like E and O in this baseline intersect is called, these points are called as the epipole points, right? But since the planes are parallel, right, and these planes are parallel to the baseline, these point will not intersect. This point P will not intersect with this baseline, and your epipoles will be at infinity in that case, right? So because there's a convention that all points converge at infinity, right? So if all lines converge at the infinity, that is the convention people go by. So for, I mean, just see, right, like if someone asks that, like if two cameras are parallel, the epipoles will be at the infinity, right? So this is a question, let's number it as 11. Consider two identical cameras K1 and K0. The optical axis coincide with z-axis with the focal length of, right, 0.03 meter with square pixels, no pinhole offset, no zero skewness. What is the expression of K, right? This is the same setting, right? You have two cameras, this is K, this is K0, right? And there is no offset, like there is no skewness, so skewness was given by this. You know that in formula for intrinsic metric, fx fy s 0 0 0, and here it takes into account from any type of translation, right? So we are only looking into fx and fy, and the focal length is given by 0.03. So your focal length is 0.03. Rest there is no translation, there is no skewness. So your expression for k comes out to be this 0.000 0 0.003 0, and then 001 here, right? Right. So now consider the point x dash in expressed with respect to the first camera coordinate, right? Suppose that x dash in, sorry, x, this is x in, x dash in is basically a rotated and the translated version of xn, right, where you have given the rotation uh, I think there is some lag. I have moved to the next line. Just a minute. I hope I'm audible, right? Okay. There is some lag in. You just lost connection. Perfect. Mm, yeah. Hello. Now I'm audible, right? Okay, thanks. Okay, so like you have a R matrix which is given to you. You have a translation vector as well, which is given to you. So there is a translation in the y direction, right? You have a R matrix. So explain in words, right? You might want to sketch a figure. What are the spatial configuration? Uh, so basically, essentially, what is happening is you want to see what is happening in this case, right? So you have a R matrix where uh, which is in this form. So what you do is like just divide everything into the like easier form, right? Everything is 1 by root 2 minus 1 by root 2 root 1 by root 2 and root. So this boil down to your cos of 45, right? So your theta is basically 45, right? You have one camera plane, whereas the other camera plane is rotated in a 45 degree, right? So this is the translation and the rotation actually means. So there is some sort of a translation along the y-axis, plus there's a rotation along with like degree of 45 degree. So your x is now updated, x is rotated by the 45 degree. So the task was basically to find out the fundamental metrics. Fundamental metrics basically helps you to map any point from the like camera 1 to a epipole line which is in the camera 2, right? And it is given by the k inverse transpose tx. This is your translation part. R is your rotation, and this is your k. K is basically your intrinsic metrics of the camera, right? So since both of the camera have the same intrinsic matrix, there is no uh, change here. So, and the k is basically a diagonal matrix, right? So not this. So the property of a diagonal matrix is, if you have a matrix k which is d d d 0 0, everything basically 0, right? Inverse of uh, diagonal matrix is 1 by d 1 by d 1 by d, everything is 0, right? This is the property you can use. So what will happen in this case is you have a k inverse is basically given by 1 by d 1 by d 1 by d, right? And the translation along y-axis, right? So the translation matrix is given by 0. So I mean, you might need to check the lecture. So this results basically come from there, 0 minus tz ty. So we will only consider the translation along the y-axis, right? Because you have the translation vector which is 0, 0.2, 0. So the translation is happening only in the y-axis. So you update your translation matrix with these two parameter numbers only, right? And your final fundamental matrix becomes 1 upon 0.03, then you have 1 upon 0.03, and this one, right? This is k inverse transpose, right? Because even for a diagonal matrix you do a transpose, it becomes the same, right? This is your tx, this is your rotation matrix which is given to you, this is your k inverse, right? Everything boils down to this fundamental matrix. So what is happening here is, so suppose you have a point in plane 1, you can actually translate that point into two up epipole line, so in the plane number 2, camera number. So you have basically k and k dash, right? So your whatever is your target point will lie on this epipole line. So now consider a point with coordinate x 0.1 minus 0.1, 0.8 and 1 whole transpose. What is the coordinate of the projection of x onto the image plane of the first camera? So first camera is basically you just multiply with the intrinsic matrix. So you get this. The point becomes you multiply with the intrinsic matrix 0.003, 0.03, and all of the others are 0, and you have, there is no translation, right? So we have seen earlier, and this is basically your, you just multiply it, you get this vector, right? Now what you want is basically you want it the epipole line l dash, right, for corresponding to this point. So what you do is, like, you just multiply everything with the fundamental matrix with this p dash, what is the point in the first camera plane. So you have 0.003, 0.003, and 0 minus 0.0.8. You can actually convert it into the homogeneous coordinate space, right? Divided by 0.8, 0.8 and 1, and you just multiply with fundamental matrix. So fundamental matrix is given by this, right? So you get a line. So what you do is you have a camera 1, camera 2 for point. So for here is your object, there is a line which is coming, ray which is coming from the object at this point. So this ray will basically, this point will basically converted into a epipolar line on this plane. So your target can basically lie anywhere on this line, right? I think just go through The lecture notes. Do I have anything else? No, I guess. I think just go through the lecture notes once so that like you get a sense of why everything, what is happening, and I think then you might want to come back and see. I think then we will be able to discuss everything in a better sense. Uh, I think this is all I have for today. If you guys have any doubt, this is the good time. Uh, and we can discuss. Otherwise, we will close. And if you have any suggestion that you want anything to be taken, then I think this is also the good time. Yeah, you can actually let me know. I'm assuming I have ton of doubt next week, so just keep posting them on the. Just create a single thread using epipolar geometry and just keep on posting them under the same thread. I'll try to pick them up from there. I agree. I mean, this is, I think, the most difficult part of computer vision. I guess everything is like very intuitive, and this basically uh, lack the clarity. I mean, for me also, it's very, the most difficult part. But like, and once you start getting a hang of it, it just boils down to like how you're doing these matrix operations. I mean, you can expect some questions from this topic because you mentioned that. Yeah, yeah. This is actually, yeah. I mean, I'm basically, I'm also studying with you only, right? Because I studied this topic, I think way back, like 2018 or something, right? But like, I've not been working on this space, so I generally work in detection, segmentation, those kind of spaces. So I am also kind of refreshing myself. So yeah, it will take some. You'll take some time to get a hang of it, but like more you go through it, more you get a bit clarity. So yeah, I think you better start early. Anything else? Anyone? Swati is there if you want to add anything, otherwise we'll close. I mean, I think there is a assignment, a quiz due for this part as well, I think, so you might want to actually go and check that out. So yeah. Assignment, yeah. Hmm. Okay, I just saw the question I actually did is present in the assignment as well. So yeah, you are lucky actually. Yeah, people who see this video might get a, what do you say, unfair advantage. But let's see how many people actually watch it. But ठीक है. Anything else, or we should we close? Nope. Okay. Thanks for joining. Keep your doubt posted, and the discussion channel will take from there. Anything, any topic apart from these, any prior thing, just let me know. Any paper if you want to be discussed, I mean, just add in the channel. Yeah, yeah, we'll take it from there. Okay then. Thanks everyone. Okay, bye bye.